Hello, everybody. Welcome back to class. Wednesday, April 8th, 2020. Yeah, let me know who's here. Say hello. Say hi in the chat. I don't know. I'm a little early. I feel like I'm usually here at 9:58. So I have an extra minute of small talk to make with nobody. So we'll see how that goes. Yes, let me know who's here. Say hi in the chat. You know the drill. James, first to class today. Lauren, hello. Jax, hey. How's everybody's isolation going? I hope it's going well. I'm sure your classes are keeping you busy, so you don't have to go out and cause trouble. Jared, hello. Pretty good. Just been streaming. Must be genetic. All right, well, we'll start up in about a minute or so. Seems like our numbers are a little bit low today. Not sure why, but that's fine. Remember that first day class, we had like 40 people. It's like, who are these people? All right, well, it's 10 o'clock. So you know what that means. It's time for the simultaneous sip. So if you have your coffee or water, whatever, ready, and you'd like to join, please join. And let me see the chat, not just the sips, but let me see where you're sipping from. North Carolina, like I am, maybe out west, maybe a different country. Where are you sipping from today? Sipping at my desk in New Jersey. Oh, that's great. Stay safe there. North Carolina, UK, another New Jersey, Charlotte, North Carolina, all over the place. New Jersey again, a lot of New Jersey. Georgia. New Jersey again. All right, so we're in section 3.9. Vermont, it's odd. Section 3.9, which is antiderivatives. Sipping from Florida. Cool, cool. Okay, so this whole, like for the last, I don't know, month, 2 months basically, we've been taking derivatives, right? We start with a function and we get a new function that tells us what the slope at a particular point is of our function. We saw there's some applications, helps us find the absolute max or absolute min, or the more derivatives you take, it tells you other information. Like second derivative tells us about the shape of our curve, concavity, concave down, concave up or concave down. So what we're going to do now is we're going to reverse everything. Okay, So we're going to take a function and ask, I'm the derivative of what function? For instance, if you had the function 2x, well, I'm the derivative of x squared. We're going to be talking about techniques to do that. That's the big idea. Okay, so we'll start with the definition. What exactly an antiderivative is, and then we'll see some examples. So a function f is called an antiderivative of a function little f if f prime of x, so if the derivative of capital F is equal to little f. Okay, so we're looking for functions whose derivative gives us the function we started with. That's the idea. So for example, if f of x is equal to, let's say, 3x squared, then capital F of x, for instance, could be x to the third. But there might be another function. So if f of x is equal to 3x squared, capital F of x is equal to, let's say, x to the third. Let's say we had a different function, g of x is equal to x to the third minus 5, and h of x equals x to the third plus 1,000. Capital F, G, and H are all antiderivatives of f. You can check. Take their derivative. What do you get? You get 3x squared. Okay, so there's not a unique antiderivative of a function. There could be a number of them, right? And you could just check. The way you verify is you take the derivative, you get 3x squared. You take the derivative here, you get 3x squared minus 0, which is 3x squared. And same thing here. Sipping from Australia, Epic Cuber 7. Sweet. Yeah, so we have, there's going to be a family of functions that are the antiderivative of f. And it turns out the functions have a lot in common. Basically, they have the main part, and then they have a constant that can differ. Okay, and I think we actually talked about this earlier in the semester. We had I gave you a true or false question as like a think about this, and we start class with it. I said if two functions have the same derivative, they must be the same function, which is not true. And we said that they have to differ by a constant. And so we're going to talk about that again today. So we'll write that as a theorem. So it says if capital F we probably need more space. If capital F is an antiderivative of a function little f, then the most general antiderivative of f is f of x plus C. Okay. Where C is just some arbitrary constant. Okay, so what does this theorem say? It says that all antiderivatives of some function little f differ by a constant. You can't have something else happening. So let's look at an example. So at this point, we don't really have any techniques for finding antiderivatives other than guessing and getting lucky. We'll talk about some techniques in a little bit, but let's see if we can guess and get lucky for a few examples. So find the most general antiderivative of the following functions. Okay, so the first one is f of x equals sine of x. The next one, oops. Well, I mean, you could solve that, but we'll put it as to the fifth. So the first one is f of x equals sine of x. The next one is f of x equals x to the fifth. And the last one is f of x equals x to the negative third. So I'll give you, let's say, a minute to try to work these out. If you have any questions, feel free to ask them in the chat. And if you get a solution for any of these, feel free to post your solution in the chat as well. Is it Thursday in Australia? You know, I have no clue. I know it's Wednesday here in the US. Maybe Epic Cuber 7 could help us out with that one. Max says negative cosine of x. That's very close. You're missing a little bit, but small detail. Plus e, yes. Good, good. Yeah, okay, so I see a few of you are getting answers, and you're making the same, common mistake. You got to get in the habit of throwing that plus c at the end, just so you capture all antiderivatives. But yeah, good. What about, did anybody get this last one? What function's derivative gives us x to the negative 3? Well, you can think about that. I'll kind of talk about this first one. Again, this is just, you're close, Jax. Not quite, though. So this first one, which function's derivative gives us sine? Remember, sine and cosine kind of bounce back and forth with their derivatives? But it's not cosine, right? The derivative of cosine was negative sine, so it would be negative cosine of x plus c. And again, at this point, we don't have techniques. This is just like a matter of pattern recognition, guessing and checking. What function's derivative gives us x to the fifth? Well, we know the derivative of x to the the derivative of x to the sixth is 6x to the fifth. So if we throw a 1/6 in front of it, you could check the derivative of 1/6, x to the 6 gives us x to the 5th. And then last, maybe this one seems tough because it has a negative exponent, but really it's the same idea. We know that the derivative of x to the -2 gives us -2 x to the -3. So let's put a -1/2 in the front. All right, and you can check. If we'd bring the power down in front and drop the power by 1, we'd be left with x to the -3. Okay, so this is just kind of the idea. Again, we don't have a formula of any techniques yet, just guessing and getting lucky. So are there any questions, or are we good to move on? Feel free to slow me down if we need to. We're right on schedule despite missing an extra week, so we're doing good. Okay, well, ask any questions if you have them. Okay, so let's write down a table of antiderivatives. So here we'll have a function. And then and a particular antiderivative. Okay, so I'll start with the basics, and then we'll. So if we have the antiderivative of, well, let's change this to d so we don't get confused. Of a constant times a function is that same constant times its antiderivative, and then again we had to add c at the end. All right, so if we have a scalar multiple in front of one of these functions, we could just kind of ignore it and just put it back at the end. The antiderivative of a sum of two functions is the sum of their antiderivatives. Again, plus a constant. You don't have to add a constant for each of the terms, because then at the end we could just group all the constants together and just say it's like one super constant. So we'll just say, just throw the constant at the end. We don't have to do it each time. Right? You could if you'd like, but it's just unnecessary details because you'd have a bunch of constants. And if you add up a bunch of constants, you just get a new constant. And so that new constant would be c here. Okay, so now those are just general formulas. This is saying, don't worry about scalars, and this says just find the antiderivatives one at a time. Now, here are the ones that are useful. Okay, if our function is x to the n, what is the antiderivative of x to the n? So here we had a couple of examples of x to the n. And how did we get the antiderivative of these? Yeah, so what we did was we raised the power by 1 and divided by the new power, which is what Jax wrote in the chat. But this works unless n equals, when does this formula not work? For what value of n will this formula not work? Yeah, when n equals -1. Right, and the reason why it doesn't work if n equals -1 is you would try to increase the power by 1 and divide by the new power. That'd be dividing by 0. We're not allowed to do that. Yeah, so we would have, if this was -1, trying to use this formula, you'd get x to the 0, which is fine, over 0, which makes no sense. And so there's a different antiderivative when of x to the -1, which we don't talk about in this class, but you'll talk about it in Calc 2. It's not hard. It's just we spend our time doing other things. Okay. Next, we could talk about the trig functions. So just the basic trig functions. Okay, and we could go through these one at a time. The antiderivative of cosine, it's asking what function's derivative gives us cosine of x, and that is I missed a plus c here, but all these should have plus c in them. We already know this next one. What's the antiderivative of sine of x? That's negative cosine of x. Okay, now this is a question for you all. What is the antiderivative of secant squared of x? Which function's derivative gives us secant squared? Yeah, and so you'd have to look back in your notes. Jack's got it. Tan of x. Good, and then just remember, we have a whole family of solutions. And last, which function's derivative gives us secant of x tan of x? That was secant of x. Okay, so this is a good start for antiderivatives. Tells us how to do a lot of antiderivatives, really, at least for the functions we deal with in this class. Obviously, there's going to be some functions that are very complicated, and it's going to need some advanced skills to figure out their antiderivative. But that's what you do in Calc 2 for the whole semester. You spend a whole semester talking about techniques to evaluate antiderivatives, basically. So let's take a look at an example. Okay, so the question is find all functions g such that the derivative of g is 4 sine of x plus 2x to the fifth minus square root of x all over x. Okay, now before you get started, my question for you, somebody to answer in the chat, is, well, we don't have any antiderivative rules that deal with fractions, right? We have a scalar multiplication, we have function addition. We don't know how to deal with this fraction. So what can we do? What can we do to this part of the, right? 4 sine of x, that's going to be easy to find the antiderivative of. But what can we do to this part to put it in the form of some of the terms in our antiderivative table? Right? Because right now we don't know how to, we don't have a rule that says, oh, we just take the antiderivative of each of the components and we're done, because that's not true. That's not how it works. Right? You would imagine, right, to take a derivative, if you have a quotient, there was some sort of quotient rule. You would imagine there's going to be some sort of equivalent rules for antiderivatives. Austin says multiply the numerator by x to negative 1. Yeah. So basically what we could do is just break this apart, right? We could write this as 2x to the fifth over x minus, and then we're going to have to figure out how to deal with that part. We treat this as two separate, we break apart the fraction into two separate components. Right, and so that is the same thing as multiplying the numerator by x to the negative 1, or divide each part by x, right? Because this is really just now 2x to the fourth, and this here, well, that's for you to figure out. Okay, so I'll give you a minute. I'll give you a minute or so to try to work these out, and then we can talk about it. But if anybody has an answer they want to share, I know it's tough to type these functions into the chat, but anything in the chat, I encourage. Even if you want to talk about something totally unrelated, it's fine if you put it in the chat. Keeps us entertained. Yeah, that looks good, Jax. All right, I'll walk you through the steps. But this was the hard part. Going from here to here is the hard part. I mean, I guess let's clean up one last bit. So 4 sine of x, 2x to the fifth over x, that's just plus 2x to the fourth. And minus the square root of x over x, well, that's x to the 1/2 over x, which is x to the negative 1/2. Okay, so we want to find the antiderivative of this function. Using part 2 here, our second entry in the table, that just says we take the antiderivative of each of the components. So the antiderivative of 4 sine of x is going to be 4 times negative cosine of x. So negative 4 cosine of x. The antiderivative of x to the fourth is x to the fifth over 5. And the antiderivative of x to the negative 1/2 is x to the, well, add 1 to negative 1/2. That's positive 1/2. And divide by the new power, which is dividing by 1/2. So we can clean this up just a bit because we have space. When you divide by 1/2, that's the same thing as multiplying by 2. So we get this. And you could take the derivative. The way you check your answers, you take the derivative. You take the derivative of what you get and make sure it's what you start with, and it's going to work out. All right, let's take a look at another example. Let's do 2 examples. All right, so the first one's quick. Actually, let's just go one at a time because this is an important skill. So find f if f prime of x is equal to x square root of x, and f of 1 equals 2. So now we have some sort of initial condition. We have some point on our curve that we need to satisfy. Okay, so my question for you is, how do we express f prime? How do we express f prime as a function that is of one of these forms? Right, because x times the square root of x, again, that's a product. We don't know how to deal with products. Can we rewrite this so it's in, one of these forms? And it's probably not going to deal with any of the trig functions. All right, so instead of having x times the square root of x, we could rewrite x, or we could rewrite the square root of x as x to the 1/2. So x to the first times x to the 1/2, that's the same thing as x to the 3/2. Right? And now we know that the antiderivative of x to the 3/2 is x to the 5/2 over 5/2. And so the question is, how do we get c? Right, we were given this fact that f of 1 equals 2. So how do we get c? Plug point in. Yeah, exactly. Yeah, it's as simple as that. We're given that f of 1 equals 2. That means when we plug in x equals 1, we should get the number 2. So 2 is equal to 2/5 times 1, so 5/2, plus c. 1 to the 5/2 is just 1. So when we saw, so this is 2 equals 2/5 plus c. This gives us that c is equal to, well, 2 minus 0.4, which is 1.6. You can write it as 8/5. Just so we have fractions. You know, we have fractions over here. Let's just keep it consistent with fractions. It doesn't really matter. You could write 1.6 if you'd like. And so our function f of x is equal to 2/5 x to the 5/2 plus 8/5. Again, feel free to ask any questions you may have. Maybe throw a thumbs up in the chat if you're following along and feel like you're gonna, do well with these antiderivatives for the rest of the semester. I don't know, just give me a little bit of feedback. All right, so the next example is find f if f double prime Thank you, Max. The only person listening. I'm kidding. Okay, so this next example is find f if f double prime is equal to 12x squared plus 6x minus 4. And we're given two initial conditions this time. Okay, we're told that f of 0 is equal to 4 and f of 1 is equal to 1. Okay, so I'll give you 3 minutes. I don't know if that's enough time or not, but I'll give you 3 minutes to work this out or try to work it out. Share any ideas you have in the chat, please. Yeah. And so I'll just be standing here in my room in silence and waiting for the 3 minutes to be over. Does it matter which point you decide to plug in first? No, it doesn't matter. One of them will be easier to work with than the other, though. So typically, if you're given information about when x equals 0, that's probably your best option. Because like a lot of terms will go to 0. But it doesn't matter. Either way, you should get the right answer either way. All right, well, I don't know if the time if it's been 3 minutes, but it felt like an eternity for me, so I'm gonna get started. Yeah, so basically what we want to do is just find the antiderivative and then find the antiderivative of that. And then we can deal with these points. Okay? So the antiderivative, so f prime, which is the antiderivative of f double prime, well, it's 12. Okay, so what we're going to do is increase the power by 1, divide by the new power. So we'll have 4x to the third plus, again, increase the power by 1. So it would be 6x squared divided by 2, which is 3x squared minus the antiderivative of a constant is just the constant times x. Okay, and now, so we have 4x to the third plus 3x squared minus 4x plus c. And we want to take the antiderivative again. Increase the power by 1, divide by the new power. Again, increase the power by 1, divide by the new power. Again, increase the power by 1 and divide by the new power. The antiderivative of this arbitrary constant, which we call c, is c times x. C is a constant, so its antiderivative is cx, plus a new arbitrary constant, which we could call d. Okay. So just show of hands in the chat, thumbs up or thumbs down, or, something else. So far, so good. Okay, now we want to find, hopefully a few of you respond, but now we want to find the values of c and d. So we use these points, okay? So we'll plug in, we can start with this first point. It's, again, like what Jack's asked, does it matter? No, it does not matter which point you use first. It's just that like one of them will be significantly easier than the other in this case. So let's evaluate f of 0. Well, that's equal to 4, just that was given to us. But it's also equal to 0 plus 0 minus 0 plus 0 plus d. Right, so we have d is equal to 4. F of 1, which is 1, is equal to 1 plus 1 minus 2 plus c plus 4. Okay, so that's just when we sub in 1. 1 plus 1 minus 2, that's 0. So we have 1 is equal to c plus 4. C is equal to negative 3. And so now we're done. We know the answer. F of x is equal to x to the fourth plus x to the third minus 2x squared minus 3x plus 4. Okay, and so notice we had to take two antiderivatives, and in order to find all of the constants, we needed 2 points. And in general, if you take n antiderivatives, you would need n points. So the more antiderivatives you take, the more points we're going to need in order to find a unique solution. All right, let's look at one last example. Okay, since we're a little bit short on time, I'm going to kind of cut out the fluff and just get to the big stuff. All right, so we have a particle moving along a straight line, and its acceleration, a of t, is given by 6t plus 4. Okay, its initial velocity is -6, and its initial displacement is 9. The question is, find s of t. Okay, so we have the acceleration is 6t plus 4. We're given a fact about its initial velocity, and we're given a fact about its initial position, and we want to find its position in general. And so I know we're a little short on time, which is why I'm rushing a little bit, or a lot of bits. But remember, the derivative of position gave us velocity, and the derivative of velocity gives us acceleration. Okay, so the antiderivative of acceleration will give us velocity, and the antiderivative of velocity will give us position. Okay, so to find position given velocity, we're going to need 2 antiderivatives. So v of t, which is the antiderivative of the acceleration, is, well, the antiderivative of 6t is 6t squared over 2, which is 3t squared. So 3t squared plus 4t plus c. And now we can plug in the initial condition. So v of 0, which is equal to -6. 0 plus 0 plus c. Okay, and now to get s of t, so v of t is equal to 3t squared plus 4t minus 6. To get s of t, our position, we take the antiderivative of velocity, and we get t to the third plus 2t squared minus 6t plus, we've already used c, so let's use the next letter in the alphabet, d. And again, we were given an initial condition. So let's plug in t equals 0, and we should get 9. So you get 0 plus 0 minus 0 plus d. And that's all we need. Okay, so just to keep it in your notes, and since we have a few minutes, maybe I could have gone a little slower. Just as a reminder, s prime or s double prime of t is equal to v prime of t, which is equal to a of t. So this is the fact we used. The derivative of position gives us velocity, and the derivative of velocity gives us acceleration. Okay, so well, that's it for antiderivatives, believe it or not. Tomorrow, we're going to move on to something that appears totally unrelated. It's called integrals, and basically it's going to start by trying to find the area under some region. Okay, and so we're going to try to find the area under some curves, and we'll see that maybe there is some connection to antiderivatives, and it's awesome. We do have a quiz tomorrow. I'll send you an email about that. It's going to be an optimization. I'll give you some practice problems to think about. Please get some sort of app that lets you submit PDFs. It just makes it easier for me and the TA to have everything on Canvas. So it's, makes grading quicker. Let's see. Smash the like button before you get out of here. So important. I'll stay around for a few more minutes to answer any questions. Already smashed it. Thanks. So I'll stay around for a few more minutes to answer any questions. But if not, good class. We'll see you tomorrow for the last class of the week. Bye-bye, Turner. What's tomorrow's shirt going to be? I don't know. You'll have to come to class to find out. All right. Well, if there's no more questions, I'm going to end the stream. Bye-bye.